Wait, there are no accidents.
All right, what's coming up in this class?
I feel like the slow decline of everyone's sanity and willpower. Going into the end of the quarter.
In real time, I see it happening too.
I think it's hit the drop off point. Or it's getting close to it. It's like, oh no.
And it hit below.
Yeah,
10.
like,
I feel like these couple of days this week is like the time to either double down and finish strong or just, it'll get done.
So we are now into sprint 4. Next week is Thanksgiving week. I'm trying not to make anything extremely important happen in person next week for those of you who need to travel. So there will be lectures on Monday and Tuesday, but they will be recorded and available to be watched online rather than the need to be in person. I will still need some people here in person so that what happened in my other class the other day doesn't happen, where I lecture to an empty classroom and feel like it's COVID all over again.
Just me, I'll be here and we'll make it.
Excellent. So what we are going to be doing today, we're going to be finishing up talking about API design, and we will be going into talking about formal verification as the last major topic that we cover. I want to get a couple dates on the calendar for us. Actually, go back and look at my email. The last week, there are going to be a couple of lectures in here from the cybersecurity perspective faculty. So there will be some cyber related lectures. They just needed a classroom where there were going to be some students in it, and I think I will be done with all of the necessary content of the class by then. So I offered this class up for that. So that'll be Tuesday and Thursday of the last week classes. Question?
When's the final presentation?
That's a good question. I actually have to look that up myself.
So is that gonna be during finals? week,
During
or
finals
that's gonna be
week,
the-
Yeah,
Is it?
so we'll have a 2-hour meeting period in here where we'll come in, give some informal presentations, and I will bring some donuts or something of that sort to make it palatable to actually come in and do that.
Is this considered a Monday through Friday class? When I was looking for
No,
finals, because I couldn't see any other schedules ever like this.
Yeah, we're gonna consider it to be a Monday through Friday class because that will,
I think it's on Thursday then.
because I think it's based on the first meeting of the week. So we consider it to be a Monday through Friday for the course.
but we don't have class on Fridays.
Correct. We don't have class on Friday, but for the sake of looking up the finals schedule, since there's overlap, you can't possibly have a class on the Monday to Friday at that time slot. So you can't possibly have any of your other courses have a final in that slot either. So just identifying a time where there are going to be no conflicts. That is true, and that's on Thursday. I'll update that and send out a Canvas announcement of exactly what day that's gonna be. But then, so that's the week of Thanksgiving, then the last week of instruction follows that. So Tuesday and Thursday will be cyber lectures, and there will be some day in that week where we can't meet in this classroom. There's something going on, and I think we will instead meet in 301 for that day. I forget if that overlaps with one of these cyber. But then that's when Sprint 4 is going to be due, and then there is final code that you will be working on. There will be no additional requirements for that final code, but it is the drop dead date for submission of anything that you want to. Be the Friday of finals. So between that Sunday and that Friday, you can just fix stuff, and anything that you fix will become points that you get for this outcome that is worth about half a sprint. Only improve your score unless you break everything. So do that. Question before we get started with that? Here's the project. Here's what I worked on. Here's the state of my sanity. It's blank.
Do we have one more quiz?
There is one more quiz that will also be in that last week.
During finals week?
Yeah, the week before finals week, the last week of instruction.
Oh,
Is the final on that Thursday?
I think so. I think it's the Thursday of finals. if what Colby said is
Yeah,
true.
I'm second guessing myself now.
I'll verify it and I'll send out an announcement so that we know for sure when that's gonna be. All right, so last we were talking about API design. We were talking about the important aspects of API. We said simple, general, regular, predictable, robust, and adaptable. We got as far as predictable. So to be predictable, this was just saying, don't violate the principle of least astonishment. If you're a user, you don't want to be astonished by what happens when you call something in an API. You don't want to be surprised by that. We got through all of this. Next is robust. We want to be able to deal with unexpected input. This means don't just have your API crash. Actually write exceptions for exceptional behavior and make sure that those exceptions clearly communicate with the end user what happened to the best of your knowledge. Because they don't have access to your source code, all they can look at is the error message from your exception. So we want to make sure that all of that functionality deals with or has some case for what happens with unexpected input. And then finally, adaptable. We want to write an API that can be extended, but we don't, again, want to ever modify that API. We want it to be extendable. If this becomes an API that gains traction and gets a ton of users, it's likely that you're going to be trying to make this as robust as possible, as large as possible, to be able to handle as much as possible. So you will be extending that API. And you never know if your API is going to become the next big thing. So you want to design for that from the beginning so that you don't go, oh no, it's starting to gain traction. Oh no, I really want to change things about it because I'm not proud of it. Your name is going to be attached to that API forever. Then make sure that implementation details don't affect the API. So if you have a couple different list types that you could use, the actual implementation details for that shouldn't affect your API. You shouldn't have different calls if you're going to use one list or another list. The idea is if there should be an interface for something, you should write that interface and make sure that all classes that implement that interface all use the same types of calls to do the same thing. So how it is done, how it's actually programmed should not affect the API at all. That way you can go change your code. You can go make it more efficient. You can go change exactly how it works and you don't have to modify the API. The big second part was resource management. This is especially important if you are using a language that forces you to manage resources like C or C++. You need to make sure that either the end user or you are responsible for each of these aspects. You don't want to not make that decision and leave it open-ended, or not have it embedded in your API that the client is responsible for the initialization of data types. That should be inherent in your API and make sure that it's clear who's responsible for the initialization, who's responsible for maintaining the state, who's responsible for sharing and copying data, who's responsible for cleaning up any memory. So for those of you who have taken a C or C++ class, you know that you have to either malloc your own memory or in a constructor construct, you have a destructor, you have to dealloc if you're in C. Who's responsible for that? Who's responsible for making sure that someone's program doesn't have a memory leak?
Nothing bad happens in C if you have memory leaks.
You want that to be inherent in your API. In that documentation, it should say, you do not need to worry about allocating or deallocating space. Or if they do, make sure that you state what the client needs to do. This is an object that needs to have its destructor called. This is an object that needs to be deallocated. Who is responsible for managing memory? Who is responsible for managing files? Who is responsible for managing any global variables in your code? All of this is important to make sure is inherent in your API. If you allocate resources, then you should be the one to free them. It should not be something like, I'm gonna allocate the memory, but I'm not gonna implement how to deallocate that memory. That's on you. That's gonna create memory leaks. And your client's gonna get frustrated with you. If you make them allocate the resource, but then you automatically deallocate it, if they try to deallocate it and it's already been deallocated, they're gonna get a frustration. Are you shallow copying or deep copying objects? So are you returning references or are you returning deep copies of objects? Something that you need to consider about an API, because again, this can't change. If you return a shallow copy of an object, and then you later determine that you really need to return a deep copy of that object, that will change the underlying return. That will change how people use your code. You can't do that. If you have multi-threaded code, it's very important to talk about how the multi-threaded code works. The last big category here is error handling. So we want to make sure that we are catching errors. If something happens, we should be throwing some kind of exception. And we should be catching that exception so that we can print out something useful. If they just get a stack trace, they didn't write the code, they're not going to be able to refer back to the code to be able to figure out what happened. If you just print a message and fail, that can be good sometimes, but in APIs, you need to potentially allow the user to save what they've been working on. Anytime something exceptional happens, a user is going to, if they didn't know how to use your API, they fed in a wrong parameter type, and now some always online service, like a database, just crashes. If you haven't been writing that to disk, if you've been storing anything in memory, anything that was in memory is now gone. So if you didn't at least allow the user as part of that error handling to try to recover something that was important and write it to disk so that it's there, or somehow if it's possible to recover from that, you should think about, how do I recover from that? How can I recover from that? Rather than just saying the easy road is to let the program crash. It's not going to create an API that people actually want to use. You want to, in general, detect at the low level, handle at the high level. This means that the error shouldn't be handled within the function or the method that is using it. Go to the level above that. What called this? Handle it there, because you may want to just recall the method. And you're fine then. You just throw away all the work that had been being done on the method and start over. The other important part of this, or I guess another important part, is that when an error occurs, you don't want to obfuscate this from the user and think, well, maybe they're going to give me some information that would lead to my being able to recover. You immediately want to report it, even if it's at compile time. This can be something like a warning at compile time. If they're using static types, if they're using generics, these might be something that the user would want to know about the program that they've written that is supposed to interface with your API. If there's something that they might not have intended, leave that as a warning. That's why those warnings exist. In case you didn't intend for this, now you know. You can go make that fix before you try to run it and end up in a state that is not what you expected. If you're going to return from something, it should be in the form that the calling function can use. That seems kind of obvious, Shouldn't have to be stated, but it's important. So if you're going to make an exception, make sure that anything that gets passed back is something that can be used. Return as much useful information as possible. That just means that let the user know everything that you know as the program is crashing. Even if you don't think that has any value to the user, you don't know how the user is trying to use your application. Worst case, they just don't use it. You can return another parameter to indicate an error. That works too. An error wrapper function can be used in something like C++. Any questions on anything so far? I'm not going over every single one of these bullet points because I feel like if there isn't too much else to say about it, I'd just be reading the slide, and I don't like just reading slides. So I identify the points where I want to add something to it. Question?
So the error that you're gonna let the user know what the error was, and then are we gonna click logs of that for ourselves?
Quite possibly, yes. But that's not necessarily part of the API. The API is just the public facing part of it. So yes, you certainly want error logs that would tell you something like, this is the method that was called when a client program crashed. And that you would log that data for your own internal use about maybe this information isn't clear. Maybe I should go change the documentation of the API, not the API itself, but to change the clarity of some of the wording, because whenever this 80% of the crashes in the code that I've published are from calling this method. Why is that? Oh, look, the documentation is actually wrong, or the language is not clear about what the user needs to be doing. That can tell you that without them having to send you an angry email about it. Yeah, great question though. So exceptions. We've already mostly talked about all of this. Not a ton here that's new. Any questions on anything on this slide? Mostly talked about all of it. The next slide has stuff that's actually worth talking about. So exceptions I've found to either be too infrequent or too frequent. It's rare that I feel like an application handles exceptions correctly. So they should be used in exceptional situations. I've certainly seen it used as a control structure, which means that if something is done, throw an exception. That's not what that means. An exception is something that you can't recover from, or at least says we've reached a point that we need additional input to be able to continue, because the information that we have leads to a crash. It is not defined how the program proceeds from here. Has anyone used go-to statements in your programs?
Heard about it, and I just know that from like Dijkstra's thesis on it, he really hates go-to.
Everyone hates go-tos for
Even
good
like-
reason. So go-to used to be a part of modern programming language, not our current modern programming languages, but in C, for instance, it was taught as something that you can do. First of all, what is a go-to?
It just goes to like a part of the code or something.
Yeah, it's an instant teleportation to a particular line of the code, which that seems like a very powerful thing that you might occasionally want to do, right? Why would that be a bad idea?
You could just manually telling it the places and.
Yes, it basically boils down to humans are prone to error. And there has to be a reason to want to do that. And our programming languages always have a way to do that. You call a method, that's a go-to. You return from a method, that's a go-to. But there's a reason for that. You're saying execute this and only these lines of code in this method, in this way, with these parameters at this point. If you say go-to, there is no such structure associated with that. You can hop between very strange points in your code in ways that can create very unintended behavior. You think you know what you are doing, and there will be difficult bugs to debug as you do this. So using exceptions, not in exceptional situations, is very similar to that. If you're going to throw an exception, basically you say, if the state is wrong, throw an exception. No, you wait for the issue to arise, you recognize that, and then you throw that exception.
Like the Java course, you use try catch for file IO. It's
You
common.
don't have to, you put throws in the method declaration. A try catch is always the wrong solution to that, because it is gross and looks really ugly. So yes, if your try catch is only for particular kinds of, try catch is great for exceptions. Try this particular thing. If it doesn't work out in a way that you expect, then catch the exception. That's great. All right, questions on any of the end of this? This is basically the end of API design. I just think that it's very much worth talking about because you will all be designing an API at some point or be part of a team that is designing an API. Even if you don't think that's going to happen, you will find yourself in that situation. And it is very important to take that seriously, to go through that design as you would the design code, really plan, use some forward thinking about how is this going to be used. Right. Where did I throw this? The problem with having too many tabs open. I'm gonna go find. I'll bet it launched it in this, didn't it? No, it didn't. I put up the next slide deck, but it's a PDF rather than. Interesting. I don't want you to launch in Edge. Whoever uses Edge for anything.
Not terrible anymore. They actually fix it, it's just, they lost that trust a long time ago.
I think it's still too. I still have issues with it.
I only use it for Discord because I refuse to install it on my desktop because I'm tired of it popping up every single time I log into my device.
So the last big topic we're going to talk about is formal verification. So this is going to be probably the most technical topic that we cover in the class, which is good because we need something technical in here. So we've talked about program correctness through the lens of writing tests. We've talked about how do we know that our program is correct. If we are testing, we have mostly said we're going to take a best guess by writing enough tests where we are reasonably sure that the program is correct. But imagine that you are responsible for something that you can't go back and edit, like a Mars rover. Once you write the code for that, you embed it onto the Mars rover, and then you launch it into space, you can't edit that code anymore. That is a very expensive process to launch that Mars rover into space and to transport it to Mars. And once it is there, you don't want to find that there is a bug. Oh no. I'm not going to Mars to hit it on the head with a shovel. I don't know about you. Once this thing is on Mars, I expect it to work. So there's really going to be no set of tests that I personally am going to be happy with in terms of making this Mars rover. I'm going to want to know that it works. I want to mathematically prove that this Mars rover, when it reaches Mars, will do what I want it to. We've talked about all the other ways that software can go wrong. If you're responsible for life and death, you probably want to make sure your software works, because otherwise you will be bankrupt. You'll never be able to find a job again, and you will be a laughingstock for future computer science courses until the end of time.
Don't call hacksmith for nothing.
So how do we do that? We know all of these. I'm gonna skip some of these slides again, because they're stuff that we've talked about in other. So we know about testing. We know that testing cannot prove the absence of bugs. It can prove that a particular kind of bug exists, but it cannot prove the absence of bugs. So have we executed every line of code for every possible input of the program in every environment and operating system with every possible dependency and every possible way that that environment could fail? For any program, that answer is going to be no. There's always going to be some bug report that comes in that is not what you were anticipating. So formal verification exists to prove a program always satisfies a particular property. We can say this for all inputs, for all environments, based on some limitations. We're going to hold some things constant, but we need to define what those limitations are. So for instance, this program is correct for all executions where this particular loop runs 3 or fewer times. Great. It's correct for all inputs when those inputs are sorted. So coming up with those limitations and testing based on those limitations can be useful. We talked about verification versus validation already. So let's take a look at some properties of correctness. Here's an example of a binary search algorithm. Take a look at this and try to understand exactly what's happening. I'm not trying to say identify bugs. I'm just trying to say we're going to follow this up with how would you know that this code adheres to a particular property? Try to understand exactly what's going on. We're trying to find the needle in the haystack. The needle is the integer that we're searching for. We're searching through an array that is a haystack. So we're going to do a binary search. We're going to look at the midpoint. We're going to figure out, is the midpoint what we are looking for? If it is not, then how does the midpoint compare to what we are looking for? If it's lower than what we're looking for, then we want to look in the second half of the array. If it's greater than what we're looking for, we want to look in the first half of the array. Then we're going to loop back around. And now there's a new midpoint based on the new array is now half of the size of the original array. We're keeping track of a low index and a high index. So we're doing this as a loop instead of as recursion. This would perfectly work as recursion as well. But if we wanted to look at this in terms of, is this correct? Is there a bug in this code? Let's first think about what does it mean for it to be correct? If you had to define that or state something that said, this binary search implementation is correct, what would you say?
It crashed.
All right. So a correct implementation won't crash.
Always find the value it's looking for. If it exists.
Okay, if needle exists in haystack, then we will return the index in haystack that we found needle. What if there are multiple needles in haystack?
This either needs to only find one instance, or we can make it work and find all instances.
What do we know about how this works? Do we have any guarantee about which needle it is going to find?
It is only going to find one instance. If it actually works correctly.
Okay, are we making any assumptions? Are we assuming that haystack is not empty? What happens if haystack is empty, if it's an array of size 0? I think this still works. So we set low to 0, we set high to 0, while low is less than or equal to high. That is true. So we're going to say 0 plus 0 divided by 2, which is 0. Ooh, but then we're looking at haystack of 0. So it's empty. We would get an error.
So we need to check.
Interesting, interesting. Are we assuming that haystack is sorted? We are. Is that stated anywhere in this code? What happens if it's not sorted? What behavior do we get?
Undefined behavior.
Yeah,
We don't know.
now
for
we have an
certain.
example. We could create an example where we don't find needle, even though needle does exist within haystack. So there are a lot of considerations here about being correct that just apply to this one binary search algorithm that don't apply in general to any algorithm that we would write. So let's say if the needle exists in the haystack, it should return the index. If there's more than one needle present, then we don't really have defined behavior about which needle we're going to return. We just return an index where needle exists. If needle does not exist, it should return -1 that says we will interpret as we did not find needle in haystack. This should always terminate, which means that this method is not going to crash. So these are all post conditions, right? This is what needs to be true at the end of an execution of this method. When we go back and look at this code, these are post conditions. If we run this code, then if it is correct, we have this behavior. So those are post conditions. This tells us what needs to be true after the code runs. The post condition is a promise that we make that says, after we run this code, I guarantee that these properties are true. We need to also make additional promises to the code about what we are going to give it. These are preconditions. So we expect that haystack is sorted. Is it going to be sorted numerically or alphabetically? We have to define what we mean by sorted. We also need to state that haystack is not null or not empty, because that will also give us unintended behavior. If we set these as preconditions, then it tells us that we don't guarantee the behavior of this method if these preconditions are violated. The post conditions will only be true if the preconditions were true and we execute this code. We don't make any claims about the post conditions if the preconditions are false, or if any precondition is false. Does that make sense? Any questions about that? This is going to become very important as we start talking about formal verification, because we're going to start making preconditions and post conditions for kind of every line of code in a program. We're going to start breaking it apart into what do we know is true at every point in time? What are we guaranteeing? So preconditions, what's true before the code runs. the promise we make. What happens if we break the promise? We don't have any guarantee. We don't guarantee the state of the post conditions if we break the promises of the preconditions. Let's talk about some different techniques for verifying program correctness. You can think of putting this on a two-dimensional chart. How much effort is it to produce this verification? And how assured are we after we go through that process that our program is correct? So the least testing, least assurance, the least effort, least assurance is testing. It's pretty easy to write some tests. At the end of writing those tests, are we assured that our program works? Not particularly, only in the ways that are specified exactly in the tests that we wrote. Executive specifications are next, runtime verification, specification-based certification, search and bound model checking, and at the very end, we have theorem proving, which is basically taking everything that you learned in discrete and applying it to not proving something in math, but proving that your program does what you say it's going to do. This is why we make you take discrete. One of many reasons why we make you take discrete is because if you end up working on something very important, it is applicable to things like proving your code works, which is very important in important code. But it's also an incredible amount of work. So who's doing the work? If we are manually verifying, then we are doing the work. The computer's doing the work if we have automated verification. How thorough is this proof? If it's bounded, then it gives us some property where we are saying this proof works, but it's a limited proof. All executions with less than 3 loops, that is a limitation to the proof. Can we run the application in a way where that loop runs more than 3 times? Yes. But we can make claims about our program. We can even prove it works in certain situations. If you get a thorough proof, then you're proving something for any execution of that program. So that is much harder to do, but it's possible. A lot of work. So the techniques, some of the techniques we're going to talk about are verification conditions, abstract interpretation, bounded model checking, for logic, and testing we already know a good bit about. So testing lets us do some bounded manual tests. And the one we're going to dive into next is for logic. That gives us the ability to ourselves verify that our program works. So it's based on CAR HOR. I'm sure he didn't get any shit for that in his entire life. But absolutely genius man. But let's talk about how he defined project correctness. We have a precondition, we have the code, we have a post condition. This tells us if the precondition is true before we execute the code, then Q is true after executing. This is basically saying if the precondition and the code, then the post condition. So we have a mathematical implication there. We can, in terms of discrete, we could turn this into P and C implies Q. So here we have some more triples. Which of these are true? Take some time, think about this, and see if we can come up with this. So if a precondition says true like this, then it's always satisfied. The colon equals is just an assignment. What do we think? First one, true or false? Who thinks it's true, raise your hand. Waiting for more hands to go up by, because of the power of persuasion. Who thinks it's false? All right, it is true. Why?
It's X is X, and X is assigned to 5, therefore then X is equal to 5.
Yeah, so we're gonna say true and X equals 5 implies X equals 5. If you assign X to be 5,
X is equal to 5.
yeah, true and the assigning of X equals to 5, you can conclude from that that the value of X is 5 after that, yeah.
Because true is the precondition, is that if you set that to false, would it still technically be true?
It would be false.
X does not equal, X is not assigned to 5, therefore.
Basically, you're
X is
saying
not-
if the preconditions weren't valid
Yeah.
and we set X equal to 5,
Mm.
what do we know? Can we conclude, do we know for sure that X is equal to 5? No. Because this code might not have even been run. So the precondition must be true, and, or we assume that the precondition happened. So in the second one, the precondition is that the value of J is A. Then the code that we execute is we're gonna bump up J. Is it always the case that the value of J is now A plus 1? Who thinks that is true? Less peer pressure this time, interesting. I always like the psychological aspects of asking people these things, fascinating. Who thinks it's false? Who has absolutely no idea?
Hey.
All right, I want to hear an argument from someone who thinks it's true and someone who thinks it's false. Yeah.
Your argument was just the precondition is that J is equal to A, then that implies that J, just exactly what it says. It
Yeah,
makes sense.
Then J is already set to A, and then
Yeah.
assigns J to itself plus 1, that is logic equivalent to saying J is not equal to A plus 1.
okay, all right. Anyone want to give me an argument for why it might be false? So the precondition is saying that that's true right before we do this. So that would be valid if we could inject some code between the precondition and the code. We cannot do that. The precondition is true right before we execute this code. That's a great point, though. If that changes people's minds, the answer is it is true for that reason. Yeah,
Just, I mean, I didn't really understand, I guess, your explanation of that, but so is J equal to J plus 1, is that gonna, like, is that gonna run and then it's gonna check if J equals to A plus 1, because say if J is equal to 2, or if J is 2 and then it's equal to A, and then you set it, is it gonna be 3 after the code's run, but then, I guess. Yeah.
yeah, 2 plus 1 is always 3.
Yeah.
So there's no way that either J or A, actually, it doesn't matter what happens to A. Before this code is run, those two values are equivalent.
Also prove this by substitution.
Yes.
Since J and A have the same values, sub in A for all the statements, then it's logically true.
We're actually going to go into a little bit of some substitution because that will end up being necessary for things that are more complicated than this. What about number 3? So the precondition is that I is greater than J. We don't know what the values are, we just know that I is greater than J. The code we're going to execute is if I is greater than J, then we will assign I to be the value of j. The post condition is that I is greater than j. Who thinks it's true? Who thinks it's false? Who has no idea? Excellent. Good to know where people land. Information is better than lack of information. So let's talk about it. We know I is greater than j. So is this if statement that we execute going to evaluate to true or false?
And that'd be true.
It's going to be true. I is greater than j, so we're going to execute the code that we are going to assign I to j. Is it possible that I is greater than j at the end of assigning I to be j? It is impossible. There is no way for that to be true. Now, if we had said if I is less than j, then I equals to j, and I equals j. Now we have a true statement, because that if statement will always be false.
Oh, the if statement we put.
Yeah, we flip the side
Oh,
of this
okay,
if statement.
yeah, and that's all.
Then, yes. no
Then
matter
based on the precondition, this is always going to be false.
Right.
This then is never going to be executed.
Right.
So we know I is still greater than j because we haven't modified anything from the precondition. So it's not just about the, you have to apply all of that logic to this. All right. We can skip. This just means basically write no code. The no op. We will need substitution for things. So let's go ahead and look at, you can read this as E for X. This means make the substitution, in this case, of 42 for J. You say I is equal to J, where we make a substitution of 42 for J. This tells you that the value of I will be 42 at the end of this. So this is a way to instantiate a variable inside of some formal logic. You could substitute a variable for another variable. You could anything, but that's what a substitution looks like. We have something slash something else. Next, we can have assignment. How is this assignment? So the precondition is that we're making a substitution of E for X. The code we're executing is that we're assigning X to be E. And as the post condition, we want to know, is P still true? If we make that assignment, then the answer is yes. So you do something like this. Questions on this? Does this make sense? So any statement you could make substituting for that, we're going to set X to be 42. Now we're going to make the substitution for this statement. So now we get 42 is greater than 0. Is it still true that X is greater than 0 after we make the assignment of that? The answer is yes, X is now greater than 0 when we set X to be 42. Because 42 is greater than 0, now X must be greater than 0 when we assign X to be 42. All right, inference rules, we know this, right? Hopefully for discrete, premise implies conclusion. If the premise is true, then the conclusion is also true. Did we never see this in discrete? Or I guess, is anyone here not taking discrete? In a galaxy far, far away?
I took.
It's been a while. So implication just says if, it's an if then. So if premise, then conclusion. If the premise is true, then the conclusion is true. And a way that we can draw this is in this way. The premise, vertical or horizontal bar, conclusion. Crap, we're out of time. Yeah, we're not gonna dive into competition yet. So I guess we'll end here and come back to this on Monday. Don't worry about it for now, but this will be something that can show up in a primitive form on post-work. So it is worth the time and effort and energy, but as I mentioned, it's okay if you have somewhere to be for Thanksgiving. I will be recording and uploading any additional lecture material from those couple of days as we go over this last topic.
Better teach him to read than my own teeth in my head.
This is just how it's applied to this. There's so much more.